Okay, so third problem here, it is actually a truss structure, right? It is belonging to structure analysis, which is one of the which is one of the challenging topic in our statics to our students. So of course, so we are going to go through that step by step. Okay, so how we can approach that? So typically the truss structure, it pro problem will give us a truss structure subject to the external load and supported by some supports. Okay, and then we are supposed to find out the a couple of actually it is unknown forces of a couple of members here. Okay, so before we get started, we need to know what is our target here. Our target is actually the the members of which the force is of interest, right? It is actually the member CE, member DE, and the member DF. We need to highlight those. Okay, so we need to highlight the member CE is here. Okay, but I need to use a we have going to highlight member CE. It's not very. This is member CE. This is member D, and this is member actually DF here. Okay, so this area, so the highlighted members of interest here. So now, given that, and we can go ahead and approach that. So basically, the idea is that we are going to use the method of section here. Okay, so of course, so if you want to ask me if I can I use my method of can I use method of joint here? Of course, we can, but if we try that, especially in our exam, it will take a lot of time because typically my method of joint requires to repeat it for joint by joint, and it will be good if we are interested in the forces in every truss members, or if the truss member is uh, close to the boundary or the edge of the structure. But if we have a few structure members of our interest, and we have a pretty big and complex structure system, then if we approach that by method of joint, it will be extremely long process. Okay, so by method of a section, essentially the idea is that we are going to draw a section here to cut through the the actually it is the members of our interest, right? Okay, so now what are the members of our interest here? Okay, so it is actually the three members that we highlighted here, right? It is actually the three members that we highlighted here. So if we have a knife to cut through that, okay. So by imagining that we cut through the three members, we actually cut the truss structure into two pieces, right? So one part is actually part A, B, C, D, and another part is E, F, G, H, right? And as long as we cut that into two parts, we can draw the free body diagram of each of the parts, right? So for example, we can take out the part A, B, C, D, and then try to analyze it, right? And in part A, B, C, D, since C, E, D, E, and D, F has already been cut, they will be replaced by the corresponding truss member forces, right? So those are actually the forces on the in the free body diagram A, B, C, D, and but of our interest. We are going to establish equation of equilibrium of part A, B, C, D, and we can solve for the unknown uh member forces. So it is basically the idea we can approach that. But please note that for A, B, C, D here, we see that at A, there's a support. And if there's a support, we have reaction forces here, right? We have we have reaction forces. Okay, so if we have a reaction forces here, and we are going to have, do we know the reaction force here? And we don't know it directly, right? So we are going to solve that. So ba basically, okay, so it is not always the case, but for at least for most of the problems, for this problem, we have first to solve the unknown reaction for forces first, and then follow the steps of method section to solve the unknown the forces of the three members here. Okay. Okay, so now we're going to approach that, and first we're going to solve. Okay, first we're going to solve unknown support forces. Okay, which requires us to draw the free body diagram of the entire structure, right? Draw the free body diagram of the entire structure, and if we have the entire structure here. Let me draw the free body diagram of the entire structure, which we have the entire structure separated from its environment, which is actually the ground, right? Okay, and then we are going to replace the supports by the corresponding reaction forces, right? So we have A, and given that the problem tell us that A is actually pink, and pink should be represented by two forces, right? So it is two perpendicular forces. It is AY and AX. In other words, another way to think about that is that along which direction or about which direction does the support uh don't allow me to move here. So if you look at the pen here, so you can think about that does it allow me to move along x direction? No. So we are going to have a reaction force along x. Similarly, does that A allow me to move along y direction? No. So we are going to have AY. So are we going to have a reaction moment at A? Since so here we're going to think about, will it allow me to rotate about A? Yes, right, because it is pin. So we are not going to have reaction. We are not going to have a reaction moment at A, right? Make sense? Okay. So now for support AH here, what are we going to have? Since it is a roller here, and the roller will only have a force that perpendicular to the direction that allow it to slide. Since the roller here can slide along x direction, we are only going to have direction force along y, right? So it is hy. Okay, and in addition to that, what else do we have on the structure? We have the external force here, right? Okay, so we also have the external force here, which is 12 kilograms. Okay, so now we're going to establish the equation for the structure system here. And how many equations do we have available for the structure? Okay, so typically, since this structure is a general rigid body model here, right? So we're going to have three equations, right? First, it is summation of forces along x direction equals to 0. Okay, so what do we have along y direction? What do we have along x direction here? We only have ax, right? So it is ax equals to 0. Okay, so second equation, summation of forces along y direction equals 0. And what do we have along y direction? We have ay, hy, both going upwards, so they are positive here. And we have the external load of 12 kips, right? And it's going downward here, so it will be negative, right? So it is all we have. Well, we have the two forces here, and what will they decide how the two forces going to uh they distribute it. Okay, so we only know that the two forces here, two forces along y direction subject, it is a summation of that equals to 12, right? As the total equals 0. And how would the two forces be they distributed? So now it becomes so the third equation of moment here will tell us that. So the summation of moment about the point equals 0. It is actually the third equation here. And typically, by taking summation of moment, we have to select a point here. About which point you would like to take the summation of moment here. Well, of course, the selection here, the selection here is not it is not unique here. However, so here you are suggested to take summation of moment about A, right? The reason is because at A we have the line of action of AX and AY all crossed the point A here, right? Therefore, if we take the summation moment at A, that means what would the contribution of the AX and AY to the summation moment about A? It equals to 0, right? Because the line of action of AX and AY all crossed A, so their moment about A equals 0. That means the two unknown forces will not appear in my third equation. I will only have HY in my equation. So that simplified, actually, that minimized the number of unknowns in my equation. So that would facilitate the solution process of my problem here. So okay, so if we take the summation moment about A here, and what full forces here will contribute to the summation moment about A? First, we have the external force here, right? Which is actually which is actually 12, and the magnitude is 12 times the distance. Okay, times the distance between the line of action and actually the point A here. Okay, so which is actually equals to, so we already have it here, right? It is a 4. Okay, times 4 here. Okay, again, do you think it is a positive or negative here? Okay, since it is trying to move, since it is trying to actually trying to so if we have our pen, if we have our pen here, we with one end fixed at A and another end we push it along the direction of the force, we are going to have our pen to rotate counterclockwise or clockwise about A. It is actually clockwise, right? It is clockwise. If it is clockwise, meaning that it is a negative here. Okay, and what else here will contribute to the summation of moment about A? It is actually our HY here, right? So we have the magnitude of force HY times the distance between the line of action to A, which actually equals to, okay, which actually equals to the total width of the structure, right? It is a 12 feet. So we have 12 feet. Positive or negative here. And again, by using the same method here, we find it is actually rotating about A counterclockwise, right? So it is all positive here. Okay, so by the three equations, you are going to first have okay, AX equals to 0. And so since the second equation has two unknowns, we are going to first leave it as it is and go to the third equation. And by third equation, what do we have? We have HY equals to 4, right? It is actually 4 pips. Then go back to the second equation, ay equals to, ay will be 8, right? Ay will be 8 here. Okay, so now we will already have the support forces, and now we can go ahead to apply method of section here. Method of section. Okay, so by applying the method of section here, we are going to so as we've already talked about is that we identify the truss members of our interest, and then we imagining that we have a knife that cut through the truss members of our interest, and the truss has already been, so the truss will be two parts, right? And then we can arbitrarily take out one of the parts to analyze it. So of course, so now you have two options. You can take out part A, B, C, D, or you can take out part E, F, G, H. So you're going to see that it is completely the same. Okay, so suppose that I take out part A, B, C, D here. What are and to draw the free body free body diagram and analyze it. So we are going to have, and again we have the free body diagram of part ABCD. So we have part ABCD here. Okay, so we know that the free body diagram composed of the object that we're going to analyze and all forces on it. What forces do you think we have on the object? Okay, first okay, so I think it is more helpful if we highlight the drawings here. Okay, so at A we have what? At A we have a support for we have a support force AX and AY, right? And given that AX equals 0, and we can just ignore it, and AY equals to 8, and it is a positive, meaning that the direction is just as what we assume it is going upward, right? Okay, we have 8 tips here. And at D we have an external force here, right? Okay, so we also have what? Given that at CD we originally have the three members connected to it, but we cut the three members, we have to replace them by the corresponding forces, right? We have a CE, okay, CE. And please note that typically, given that we don't know the forces here, we typically assume that it's tension. So tension is going away from my joint here. Okay, so at D we have FD, and at DF we have FDF, right? Okay, okay. So now it is actually the all forces on it. So at least if we look at this part of the structure, how many equations do we have? Well, since it is a general rigid body model here, so we have three equations. How many unknowns do we have? We have actually it's just the three unknown forces here, right? It is also the reason why we always talking about when we have the massive section cut through the structure, we should ensure that we expose no more than three unknowns at once. Otherwise, we will get ourselves into trouble, right? At least temporarily. Okay, so here it is also the reason why we only have the since we only have the three unknowns, we directly cut through the corresponding members and we expose the three unknown forces here. We can establish equations of them right now and to solve them. Okay. So again, it will be the same. So we are going to have summation of all forces along x direction equals 0. And what do we have along x direction? So we have FCE, right? We have FCE. We have FDE, but since my FDE it is actually inclined, and we have to decompose it, right? Okay, so if we decompose it and we need to know at least the slope or the direction or the orientation of my member member DE here, and how we can how we can they determine it. Okay, so that would require us to make use of the information of the geometry of the structure. And please note that DE here is actually belonging to the triangle DFE, right? So actually it is belonging to the triangle DFE. And we have the set DF equals to 4. We have the set EF equals to 4. It is actually equilateral triangle here, and it is, please note, it is also right angle triangle, which means actually the slope of DE can be denoted as small triangle 1 1, right? Okay, so it is a small triangle 1 1 here. Okay, which means, or in other words, actually the angle between DE to the horizontal direction is 45 degrees here, right? But actually, either way, if you denote the slope or the angle, it will be completely the same. Okay, so now I have the x component of FDE, which actually equals to, okay, so we have the which is actually equals to the hypotenuse or the magnitude of the FDE times the ratio between the base 1 of the small triangle here divided by the summation of the square of the base and head, which both are 1. Okay, so actually, if you calculate that, it will be 1 divided by square root of 2. And positive or negative here of the component, since it is going towards the right, it is positive, right? It is positive here. And what else do we have? We have FDF here, right? We have FDF here, and that equals to 0. Okay. Okay, so this is actually our first equation, and for second equation, summation of forces along y direction equals 0. And what do we have along y direction here? Okay, so if we look at y direction, we have at A we have 8 going up, at D we have 12 going downwards, so it is negative here. And in addition to that, what else do we have? Okay, so we have the y component of FD, right, going upward, and its magnitude equals to the head 1 divided by square root of the base square root of summation squares of base of the head base and the head of the small triangle, right? And it equals 0. Okay, and then we have summation of forces about a point. So actually, the summation of moment about a point equals 0. Again, it becomes the question about at which point are you going to take the summation of moment? Okay, so here actually the choice available are infinite. But to make our life easier here, we are going to choose the point that where we have the most actually the line of action of the most unknown forces cross, right? That is actually D here, right? At D, we have unknown force FD and FDF all cross D. So by choosing the point at there, we are going to have all of those will not contribute to the summation moment about D. So they will not appear in the equation, right? Okay, so what will contribute to the summation moment about D? So we're going to have first it is a support force at A, right? It is actually 8 times, okay, the distance between the line of action to D, right? It is actually equals to 4, right? Okay, times 4. Positive or negative here, since it is trying to rotate, okay, since it is trying to rotate clockwise, right? So it is a negative. Okay, so what else do you think it is contributing to the summation moment about D? So we have FC, right? we have FC, okay, times the distance between the line of action, and D here, which again equals to 4, right? If we could go back to the structure, again equals to 4. Okay. Positive or negative here. Again, it is trying to make our structure rotate clockwise, right? It will be negative. Okay. So now we have the 3 equations. We can go ahead and solve that. Okay. So, well, here actually, of course, you can try to use matrix inversion to solve the problem. But if we solve that by hand, it is not very hard. As we can go with the third equation. By the third equation here, we are going to have FCE equals to, it will equals to -8, right? It will equals to -8 kips, right? Okay, so now if we go back to the second equation, since it is another equation only have one unknown, so we can solve that. DE equals to, okay, actually it will equals to 4 times the square root of 2, right? Okay, so it is 4 times square root of 2. It's actually 5.66 kips. Okay, so now we can go back to the third equation. It has 3 unknowns, of course, but we have already solved the 2 of those. We substitute the 2 unknowns back, and we're going to have FDF equals to, okay, we're going to have FDF equals to 8 minus 5.66 divided by square root of 2, right? We're going to have 8 equals to, here it is. Okay, so it is the actually this answer of the third it is the answer of the third problem here for truss structure analysis. And if you are looking at the steps, you are going to see that generally it is actually so we applied the method section here, and we first get our self prepared for the structure analysis. We solve for the unknown support forces, and then we highlight the members of our interest. We imagine that we have a knife cut through the members, and the structure separated into 2 parts, and then we can take out a part, draw free body diagram of that. So that free body diagram may contain the unknown support forces. So, but we've already solved that. So we are only going to have the 3. We are only going to have the unknown member forces, and then we can establish equations for the equilibrium of the part of the structure. Right here, it is actually part A, B, C, D, and then solve for the unknown member forces. Okay,